In this video we're going to see how to sketch the curve of this function 3x to the fourth minus 8x cubed plus 6x squared plus 5. The most important part of sketching a curve is to find the stationary points and determine the nature of those stationary points. The first step is to take the derivative dy dx using the power rule. 3 fours are 12 and the index drops to become cubed. 3 times negative 8 is minus 24x squared plus 12x, and the derivative of the constant is nothing. Now when the stationary points occur, the graph levels out, it flattens off, which means the gradient is 0. So we let dy dx equals 0. 12x cubed minus 24x squared plus 12x equals 0. And we have to solve this. At first glance it's a cubic and we think that's a bit hard to solve, but then we notice that there's a common factor of x and a common factor of 12. So the step to solving polynomials, or the general approach, is to factorise. So by taking a common factor of 12, I'm left with x squared minus 2x plus 1. Now I've got something a lot better. I recognise that I could use two numbers that add to give this and multiply to give this. The two numbers would be negative 1 and negative 1. Negative 1 added to negative 1 is negative 2, and negative 1 multiplied by itself is positive 1. So this becomes 12x, x minus 1, x minus 1 equals 0. Now that we have factorised, we apply the Null Factor Law. Now think of this as 12 multiplied by x multiplied by these two factors. Because it's a string of things multiplied, it's a product, each of these is a factor, and when factors multiply to give 0, at least one of them must be 0. Now, clearly 12 can't be 0, so we could say perhaps x equals 0, or perhaps x minus 1 equals 0, in which case x equals 1. Now this is a repeated factor, it won't give a different solution. There's two stationary points. The next thing to do is to calculate the value of y, the value of the function for each of these. So we actually get the coordinates to mark on our grid. Well, in the case where x equals 0, y would be 3 times 0 to the power 4 minus 8 times 0 cubed plus 6 times 0 squared plus 5. Clearly that's 5. So we have a stationary point at 0, 5. Now that just happens to be the y-intercept as well, because it by coincidence turned out to have a stationary point when x equals 0. What about when x equals 1? We would have 3 times 1 to the power 4 minus 8 times 1 cubed plus 6 times 1 plus 5. So that's 3 minus 8 is negative 5 plus 6 is 1 plus 5 is 6. So we have the value of 6. This stationary point occurs at 1, 6. And to mark that on my grid, now this is a sketch. It doesn't have to be drawn to scale, but 1 would clearly be a step to the right, and 6 would clearly be higher than 5. The steps on my scale are not exactly equal, but it's a sketch. No one's going to be too upset as long as the relative space is correct. Now we have to determine the nature of these stationary points. We do this with a second derivative test. So the second derivative is d2y dx squared. Now if we remember, the first derivative was 12x cubed. 3 times 12 is 36, and it'll be x squared. 2 times negative 24 is negative 48x. And the final term will be plus 12. We evaluate the second derivative at each of these points, so 0. Let x equals 0. The second derivative, this will be 0, this will be 0, it's positive 12. And when we have a positive value for the second derivative, it is a minimum stationary point. You can remember that by drawing a happy face with plus signs for eyes and a nice little smile. Let x equal 1. The second derivative. This will be 36. 48 minus 48 plus 12. This comes to 0. Now, when we have 0 for the second derivative, we have a point of inflection. The curvature changes. And I sometimes tell my students to remember this with a person who's got a wobbly smile and little zeros for eyes, as if they've just had a big surprise or a big fright. So taking this information back to our grid, we know these are stationary points, so we know the gradient is 0. This one's a minimum, so the graph must be coming down to this point and then starting to go back up. This one is a point of inflection. So this one, there must be, it's not a max, so it's going up to this point and then it continues to go up. Now that I've got a rough idea, I'll sketch that in. And that's my sketch of this polynomial, marking the 2 stationary points. And if I check on my graphics calculator, it's pretty much the same.